lecture is bug algorithms. So last time we had last time we had seen this chart, like robotics in general can be categorized into three different like categories. One is the theory part of robotics, next is the simulation part, third is the experimentation part. So in theory, you basically formulate the theory, you come up with different algorithms, then you test it out on simulations, and if it works correctly, then you deploy it on real hardware or real robots, and you can get your robot to do whatever task you have in mind, right? So we had discussed, right? For robotics, there are several prerequisites required for in linear algebra, probability, control theory, optimization, calculus, and so on. But like I said, for this lecture series, you won't be requiring any of this prerequisite. If you know, it's good, but for the sake of this lecture, you won't be needing it for the time being. And we are specifically targeting this motion planning aspect of robotics. So we had discussed last time that motion planning can be broadly categorized, can be characterized into four aspects. First is the navigation, which is the problem of finding a collision-free motion for the robot system from one configuration to the other, right? Second is the coverage part, like how you have an environment. The task is to cover each and every point in the environment, in the space. That is the coverage problem. Like you have the vacuum cleaner, which needs to cover entire area, or you have the security guard. They need to monitor the entire region that they are assigned to. Third is the localization task. Localization is basically you are using the map to interpret sensor data to determine the configuration of the robot. The robot needs to know its own position, where it is, by looking at the objects, nearby objects around it. And the nearby objects around it has some global positioning system. And looking at these obstacles or the objects, the robot can pinpoint its location. That is called as the localization problem. And fourthly, we have the mapping problem. Like a robot knows its local position, but it has no idea of the map around it. So when it goes and discovers new obstacles, new objects around it, it forms a memory map around it. So the robot has a map of it. So this is known as the mapping problem. You're basically exploring and mapping the environment. So these are the four broad categories. We would be covering the navigation aspect and the coverage aspect of it. So why bug algorithms, and what exactly is bug algorithm? So bug algorithm is basically a class of simple and intuitive problems which require minimal mathematical background to implement, to analyze, and to perform different tasks. So the task we have today is we have a robot, a point mobile robot. We want to navigate it from a start location to a goal location, but the environment we have around us is unknown. These bug algorithms are sensor based, right? So the robot has something known as a contact sensor or a tactile sensor. So the edges of the robots are filled with these tactile sensors, so that when it touches the obstacle, the robot senses, okay, there is an obstacle. Only on contact, it can sense it. So it is when it is touching, or it is really close to the obstacle. Only when the sensors can detect the objects around it. And these bug algorithms will have two motion primitives. First is they either move in a straight line or they follow a boundary. And what we say is that these simple algorithms give a guarantee, a theoretical guarantee, whether a particular goal is reachable or not reachable. So, okay, we'll start with bug algorithms. So let's look at what's special about bugs, right? So we know that most of the planning algorithms that we have, planning is going from point A to point B. They assume a global knowledge in the sense that the robot has the idea of the entire environment it is navigating. It knows the exact precise position of all the obstacles, all the walls in the environment. So we are not assuming any global knowledge here. The bug algorithms, we are assuming only local knowledge. We only know our current location at time t, and we know the location of the goal where we want to reach. And the goal is a global goal. And we don't care what the environment we have around us. The environment is something very random. We have to go from point A to point B and navigate it around it. We should not hit any obstacles, and we should find a collision-free path to the goal. So these bug behaviors are very simple. They have two motion primitives, like I said. They will either follow a wall, like left or right, or they'll move in a straight line towards goal. So we'll look at different bug algorithms. So we are assuming that bug one and bug two, they assume tactile sensing or contact sensing. And tangent bugs deals with some sort of a thing called as finite distance sensing. We'll discuss that in this lecture. So for the purpose of bug algorithms, you can imagine this robot. If you want to imagine something practical, imagine this robot known as a Roomba robot. So this robot basically is a smart robot that is used for vacuum cleaning. This is basically a vacuum cleaner. It has some sort of motion sensors around it. So whenever it senses some sort of dust in the house or something, it will go to that area, it will mop it up and then cover different area. So this can be assumed to be something that uses a bug algorithm. So consider this to be a point mobile robot, okay? Because they have like very limited sensor loaded into it, and we'll follow some very simple planning algorithms. So what we want to say is we want to go from point A to point B, and the objective is we should not hit any obstacle on the way, right? Okay, so let's look at the bug algorithms. Okay, so we have some unknown environment. We have the start location, which is the location of the point robot. It knows its location at each time. It knows its goal location. So if you know the start location, if you know the goal direction, a goal location, you can always find the direction towards the goal, right? You can form an equation of a straight line. You can find the distance from start to the goal position. So a robot can basically measure the distance between point X and point Y because it knows its start position, it knows its goal position. Otherwise, it has local sensing, like it can sense walls, obstacles, and different encoders or objects that you have in the environment. And we are assuming that the world is reasonable. Like there are only finitely many obstacles. We don't have infinite obstacles, and we should be able to reach the goal within this finite obstacles, right? So these are basically the bug algorithms. This is somewhat inspired from how some insects move along because they basically move straight if they hit a wall. Like if you have seen ants, so ants tend to move in a straight line until and unless they hit something, then they follow that wall. If it hits a wall, it moves on the wall. So it is inspired from that. That's why we are calling it as a bug algorithm. So we'll look at something to start with. We look at something called as the bug zero algorithm. So we know, right? The agent has known the direction to the goal and it has local sensing. It can sense something only when it touches it, right? So the bug zero algorithm is very simple. It's like you head first is you head towards goal. If you touch any obstacle, you follow that obstacle until you can head towards the goal again and continue. This process goes on till you reach the goal. So here it's a start location. This is the goal position. So you move in the direction of the goal. You move in this direction because this is pointing towards the goal. Then after you hit this obstacle, you are basically, you have to turn either left or either right. But that left right turning has to be fixed beforehand. The turning direction should be fixed beforehand. Like if the robot is turning left, it should turn left throughout. This is something that the user has to decide beforehand. This is how the tactile sensors have been designed so that the direction is fixed beforehand, but you have to move towards the goal. If you hit an obstacle, you follow that obstacle. Like here, it hits an obstacle, it follows that until it sees a straight path to the goal. If it sees a straight path to the goal, it will simply move towards the goal. So this is a very simple algorithm known as the bug zero algorithm. Okay, now I'll ask you a question. So what do you think? Do you think this kind of algorithm can generalize to any obstacles? What do you think? Do you think this algorithm, something very simple, like go here, follow obstacle. If it finds a straight path, go towards it. Do you think it can, if there is a path that exists from the start to the goal location, do you think this algorithm will be able to always reach the goal? What do you think? Anyone? Hello, you can hear me, right? No one? Okay, fine. I'll tell you. It's like what kind of map will foil bug zero? So let's say we have this sort of a map. Okay. You start from here. Let's say you're fixing that you always go left. You start from here, you go left, you move here, you see object, direct path towards the object. You go here, you again hit the obstacle. You have to follow left again. You follow left, 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 and then you're always stuck here. You see obstacle, you follow this here, you go here. You're basically stuck in a loop. You can't reach the goal using bug zero algorithm, correct? So there is certain limitation to it because it is essentially always following a left direction. So in this obstacle configuration, it can never reach the goal. So this is one basic defect in what we call as a bug zero algorithm. Again, I'll state bug zero algorithm. What it does is it moves in a straight line. If it hits an obstacle, it follows that obstacle. If it sees a straight path towards the goal, it moves towards that. It has two motion primitives: go to goal or follow the obstacle. These are the two motion primitives, and this is what bug algorithm gives us. So what do you think? Do you think we can improve on this? How can we improve on this so that when we develop something called as a bug one, bug two, bug three, like the basic limitation, right? Because it is turning left always, or let's say if it's always turning right, so it will go here. It won't ever reach the obstacle. It won't even ever reach the goal. So what do you think could be one possible fix? Let's discuss. Anyone? I can't read the chat. Sorry, you have to unmute. Maybe let's see. Okay. Sumit says we can algorithm approach right direction near goal. But how do you determine that? How do you determine whether it goes right or left? You have to do it smartly, right? You can't change it midway. It's like you either go left, you either go right. So if let's say you're deciding to go left from here. So you go from here, you go left, and you keep going left. If you decide to go right, you go here, take a right, and just move along this. Okay. So, okay, this can be reached if I take a right direction. If I start with right, I can always reach the goal. But the question is like, what if I flip this obstacle? Then I can't reach with right. I have to reach with left. So you see, this algorithm can't be generalized for different configuration with a fixed obstacle following direction. Bug zero fails to generalize the motion from start to goal location. So this is one major limitation that bug zero algorithm has. Okay. Any questions so far? Bug zero is clear, right? Okay. I'm assuming since you have no questions, I'll just move ahead. Now, okay. We know that there is a limitation, right, in the bug zero algorithm. Like it can always get stuck. If we design some environment, we can always create an environment so that the algorithm can get stuck somewhere. But we have known direction to the goal. We have otherwise local sensing. What if we add something called as a memory to the point robot? Okay. So that's where bug one comes in. It's an improvement over bug zero. So the algorithm is as follows. You head towards the goal. If an obstacle is encountered, you circumnavigate it and remember how close you get to the goal. Then you return to that closest point by wall following and continue. It's like once you touch an obstacle, you circle the entire obstacle. You circle the entire obstacle. You started from here, you circle it, you end here. That's when you know that you have completed the full obstacle tour. And while you're encircling it, you're storing the information, like which location is this, you're storing this location, this, all the different locations, you're storing it in your memory. And after you have stored all these locations, you can store it in an array. So after you stored all this location, then you want to figure out, like, out of the locations that I have stored, which location is closer to the goal point. So here, this location can make me reach the goal position fastest, or you can say it's the nearest distance, the shortest distance from this location to a goal location. So you cover the entire environment, you reach here, then you go back to that place, then you move ahead. Again, you cover the entire obstacle, you store everything. You know that this point is the shortest distance to goal point. Then you again go back here, and then you go to the goal. Okay. So this is what bug one algorithm does. It basically wants you to circle the entire obstacle, store each and every data point that you have, and then from the shortest distance that you have, you go towards the goal. So what do you think? Do you think this algorithm is complete? Like, if I give it any sort of obstacle, do you think it can generalize to it? Anyone? Do you think bug one gives me a complete path? Like, if I give it any sort of obstacle configuration, it can always reach the goal point. What do you say?
So it can reach the goal, but it takes some time.
Yes, that's true. So let's say we are not considering time at all. We are just looking at completeness. Time को भी छोड़ दो. Can it reach goal for every configuration? ऐसा कोई configuration आप बना सकते हैं जिससे ये goal position पहुंचे ही नहीं. So you are saying that it can always reach the goal. Am I correct?
Yes, sir.
No, sir. It's not
Okay.
always correct, because there is some disadvantage of this also.
Disadvantage as in which way? Is it in the way that yes?
Time
Please.
waste.
That's true. Let's forget time right now. Let's say we have all the time in the world, but can we reach the goal? That's the whole point. Let it take whatever time it takes. Will it always reach the goal?
Maybe, sir, and maybe not.
Acha. So I'll tell you. Okay. So this is basically what we call as a complete algorithm. Okay. This algorithm ensures that it will always reach the goal. So that's why we call bug one to be a complete algorithm. If we give it a start location, if we give it a goal location, we give it like do bug one algorithm. So you go here, you circle every point, then you reach the nearest distance, you again circle everything, and then you go to the goal. So right, like one of you said, the disadvantages, of course, it will take a lot of time. Like, let's say we are here, we know obstacle is here, but still we want to cover in the entire point, and then you decide, okay, this is the nearest point, and then you leave for the goal. So the disadvantage is, of course, you are meaninglessly traveling extra distances to reach the goal point. So there is an advantage and there is a disadvantage also. Advantage is that no matter what configuration you give, it will always reach the goal location. The disadvantage is that it takes a longer path, and that will take a lot of time. Right. So, okay, summarizing what bug one does, it starts from here. If obstacle is encountered, you circumnavigate it. You circle the entire obstacle. You store the location of each point that you have visited. You store it in an array. And then basically from that array, you determine the location from which the goal position is the shortest distance. The goal location is the shortest distance. Then you go to that location, then you move towards goal, and so on. Okay. So this is the bug one algorithm. Now, okay, let's give a bound. Okay. On what bug one algorithm, what do you think would be the shortest distance a robot can possibly take, and what could be the longest distance that a robot can possibly take? Okay. So I'm assuming here that D is the straight line distance from start to goal. This is the start location. This is the goal location. The straight line distance is D. And Pi is basically the perimeter of the iron obstacle. So this is P1. P1 is the perimeter of this obstacle. P2 is the perimeter of this obstacle. So what's the shortest distance it might travel? Like any configuration, what could be the shortest distance it could travel? Like it's the lower bound. Okay. So you have the distance, straight line distance, and you have the perimeter of each obstacle. I'm asking here for the lower bound, like the least distance that it should travel, like the lower bound and the upper bound. Okay, I'll simplify it further. So the lower bound is basically like from start to goal. We assume that we can say that there are no obstacles. It will go directly from start to goal. It doesn't hit any obstacle in between. So the least distance it should travel is distance D, right? And then what could be the upper bound on this? Okay, let's discuss this. I'll move to the next slide. Yeah. Like I said, the lowest distance it should cover is D. Like if from start to goal, there are no obstacles, it will move in a straight line. Okay. And what could be the upper bound? What could be the longest distance it might travel? So it's like it will travel distance D. D is basically the distance from start to goal. But you are circling the obstacle once, firstly. So let's say you are traveling the entire perimeter, the entire length of this obstacle. It's 1.5 times the so the distance on each obstacle it covers is basically 1.5 times the perimeter. And then basically for each obstacle you encounter, you again perform that thing. So the upper bound on this is basically D plus 1.5 times sigma pi. This is clear, right? Why at max we are taking this to be 1.5? Because we are covering one obstacle for the entire perimeter, and then at max we have to travel half the distance if it is exactly opposite to that location, right? So the lower bound here is D. The upper bound here is D plus 1.5 sigma pi. So this is what bug algorithm is about. So we know, okay, it is complete, but there is a problem. It travels a lot of distance. Like this is the worst case possibility. At max, it will have to travel 1.5 times the perimeter. If we have a very huge obstacle, then it will take a lot of time to reach the goal. Okay. So is there something better? Can we do better here? So we'll look at something called as a bug 2 algorithm. So this is again an improvement over bug 1 algorithm. So the way it works is as follows. Even here, there is some memory storage. It's like you have the start location, you have the goal location. You can form a straight line, okay? And then you store in the memory of each points in that straight line. You can construct an equation of a straight line if you know the 2 points. You basically discretize all these points. You know all the points that lie on this line. So the algorithm is like this. You move in that line, which we'll call as the M line. You move along the M line. Once you hit an obstacle, you follow the obstacle until and unless you reach the M line. You again follow this. Again, you follow this. Once you're back on the M line, you move towards it. And then you reach the goal. So this is what bug 2 algorithm does. Now, okay, again, this question. What do you think? Do you think this algorithm is complete? Do you think it will always reach the goal position, irrespective of whatever obstacle configuration I give? So like here, I can clearly see, right? It is not meaninglessly traveling in this part. It is always going towards the goal with lesser distance compared to bug 1 algorithm. So do you think this algorithm is complete or not? Complete in the sense, does it guarantee that if I have a start point and a goal point, it will always reach the goal point?
Yes, sir.
It'll always reach.
Yes.
You're saying. Everybody agrees? You all think, right? It'll always, it guarantees, right? It'll always reach the goal point. Right?
Yes, sir.
So the answer is no, it won't always reach the goal location. Okay. So look at this obstacle configuration. This is the start point. This is the goal point. It will follow this M line. It hits this, it goes left, moves left. It again follows this M line, move towards it, moves left, and so on. You see, this is stuck always over here. So in this obstacle configuration, it will not work. So I can't say this algorithm is complete, okay, because I have just shown you one case where it won't work. It will always get stuck in this. It won't reach the goal location at all, right? So bug2 algorithm, while it's simpler, while it travels a lesser distance, but the thing is, it does not guarantee completeness. Okay. So again, let's look at this obstacle configuration known as a spiral. Okay. So it's like you have to reach here. This is the goal location. This is the start. This is the goal location. So you move here. You follow this distance entirely till you're on the goal line, and then you move towards here. If you go to the left, here, if you go towards the right, let's say you move here, you move in this direction towards the goal line, you move here, 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 and then once you reach here, you move towards the goal. So you see how bug2, though it looks simple, but in such kind of configuration, which we call as a spiral configuration, it will get complicated, right? So like here, if I choose to go right from the beginning, I go here, I make a full round of all the obstacle around it, and then only reach the goal. Okay, so these are the two different algorithms, and we have discussed the different limitations. Bug1 algorithm, while it's complete, it's inefficient. Bug2 algorithm is efficient, but it still is incomplete. There are certain limitations to it. So let's compare bug1 and bug2. So we have decided, okay, bug0 is something very simple. We are not looking at bug0. Bug0 is, in most cases, it will always get stuck. Cool. So we are only looking at bug1 and bug2. So here we want to see how these two compare. So we'll look at two positions, two obstacles, in which bug2 beats bug1, and in another environment where bug1 beats bug2. Okay. So in the example we saw, okay, bug2 follows this red path, while bug1 follows this huge yellow path, right? You can clearly see that bug2 beats bug1, right? So now where do you think bug1 will beat bug2? You'll say, okay, simple. You saw, I already showed you this example. Here, bug1 will always reach the goal position. Bug2 will not. But okay, let's look at this environment. This is start, this is end. Here, bug2 will never be able to reach the obstacle. Okay. Or even if it reaches, it will follow meaninglessly longer path, and sometimes it may also get stuck at some positions. But bug1 algorithm, it will entirely circle this full environment and then determine which is the nearest position to the goal and then leave from there. Here in this case, bug1 beats bug2. So you see, with complicated environment, bug1, while it is inefficient, it still provides a completeness. It still provides a theoretical guarantee, okay, it will reach the goal position. So that's where bug1 beats bug2. But let's say if you have some very simple environment, then obviously bug2 is better because it follows a shorter path and it can do our task efficiently. So this is basically the comparison between bug1 and bug2. Okay, again, we'll look at the analysis. We look at what could be the lower bound and what could be the upper bound of these bug algorithms, right? So again, what do you think could be the lower bound? Lower bound, again, we can say, right? We have a start location, we have a goal location. There are no obstacles in between. It's only a straight line. The lower bound here is again B. What do you think would be the upper bound here? Anyone? Like, what do you think? After hitting each obstacle, what is the max distance it can travel on that obstacle before reaching the goal position. Okay, I'll tell you what it is. So here it's capital D, the lower bound, and the upper bound in this case is basically D plus pi by 2. By 2 is because it's like once you hit an obstacle, at max you have to travel half the perimeter of that obstacle, right? To reach to the M line, whatever you have. At max, you have to travel half the perimeter. And Ni is basically how many times that particular line intersects that obstacle. So it's like if the line intersects that obstacle twice, so you multiply that because you will anyway be traversing that perimeter again. So this P by 2 is basically multiplied by the number of times it hits, the line hits the obstacle. And from there, you basically determine the upper bound. So the upper bound here is basically D plus N by 2 Pi. This is the maximum possible distance that bug2 algorithm can travel. Okay. So let me just quickly summarize what we have. We have been looking at bug1 and bug2 algorithm. Bug1 is an exhaustive search algorithm. Bug1, it looks at all choices before committing, right? Bug2 is basically what we call as a greedy algorithm. What the greedy algorithm does, it basically takes the first thing that looks better. In many cases, we know that bug2 will outperform bug1, but bug1 has a more predictable performance overall. So you all agree with this, right? Like there are certain points when bug1 is advantageous, and there are certain points when bug2 is advantageous. So you see, a simple motion planner, like going from start to goal, can the analysis becomes complicated as we look more and more detailed way, right? So this is what bug1 and bug2 is. Now we'll look at something more realistic, right? So what we saw here is basically there was a global goal and there was a contact-based wall following, right? But the reality is, right? The reality is like we can't possibly have a contact-based range sensing, right? Always, because at some point, if you are in contact with something, the applicability is limited. You are touching somewhere, you're following this. So in reality, when we look towards a more realistic bug sensor, what we deal with is basically we are looking at some sort of a range sensing device that lets us look ahead, but with some finite range and with some finite resolution. So here we are assuming that we have something called as a range sensor. What a range sensor does is basically at a particular point, you are able to see some distance ahead. You can sense everything. So if you have a range, you have circular range around the robot. If any obstacle falls within that range, the robot can determine that obstacle and can decide, okay, I don't want to go there. So this is one improvement. Earlier we had a contact-based wall following, but here what we are looking at is some sort of a range device. We are assuming that the device that we have has a range sensor. So we'll look at something called as a more realistic bug sensor. Sir, we have only 2 minutes left. Do you want to start the Zoom meeting again, or should we wait for it to end? Okay, let me continue. If it ends, we'll again join this link meet. Okay. Anyway, I have like 3-4 slides. We'll end it in the next 10 minutes or so.
Sir, can we reschedule or relogin?
So whatever you say.
Okay, so okay, all guys, I will reschedule this meeting. Okay, please rejoin.